Hi, I'm Detective Incognito. Welcome to another investigation. I explore strange events, forgotten discoveries, and questions that still challenge what we know about our world. What you're about to hear might change the way you see everything. In a laboratory in Sweden, scientists created light from absolute emptiness. Not from atoms, not from chemical reactions, not from any visible source of energy. They generated real photons from quantum vacuum itself. Empty space that should contain nothing somehow produced measurable particles of light. This wasn't theoretical speculation. This wasn't mathematical abstraction. It was experimental observation that fundamentally challenged how we understand the fabric of reality. The discovery proved that vacuum isn't empty at all. It seethes with invisible energy that can be converted into real particles, under the right conditions. This is the story of how physicists spent 60 years pursuing an impossible prediction, and finally witnessed something that should violate the most fundamental law of physics: the conservation of energy. If you've ever wondered whether empty space might contain hidden power, this experiment proved it does. Subscribe now to discover how quantum mechanics revealed the universe's most counterintuitive secret. Like this video if you want to understand why nothing is actually something. The story begins in 1948, in the Netherlands. Hendrik Casimir was working at Philips Research Laboratories, investigating fundamental physics. His original objective was understanding forces between polarizable molecules. The mathematics led him somewhere unexpected. Casimir calculated that two perfectly neutral metal plates placed in perfect vacuum should experience an attractive force. Not from gravity, not from electromagnetism, but from quantum vacuum fluctuations themselves. The prediction seemed absurd. How could empty space generate measurable force? Casimir's explanation invoked virtual particles. According to quantum field theory, vacuum constantly spawns pairs of particles and antiparticles that appear momentarily, then annihilate. These virtual photons exist too briefly to observe directly, but their effects should be measurable. Between two plates separated by nanometers, only certain wavelengths of virtual photons could exist. Outside the plates, all wavelengths remained possible. This imbalance created pressure difference. More virtual photons pushed from outside than inside. The plates should attract each other, with force inversely proportional to the fourth power of their separation. Casimir published his theoretical prediction, but the force was extraordinarily small. Measuring it would require technological capabilities that didn't exist in 1948. The idea remained purely theoretical, a curious prediction waiting for experimental validation. For nearly half a century, Casimir's prediction existed as mathematical curiosity, without empirical confirmation. The challenge was formidable. The expected force between plates measured in piconewtons, requiring extraordinary precision to detect. In 1996, Stephen Lamoureux at the University of Washington finally developed an apparatus sensitive enough to test Casimir's theory. Lamoureux's experimental design used a spherical lens positioned above an optical quartz plate. Both surfaces were coated with copper and gold to create conductive boundaries. The lens was mounted on a torsion pendulum, capable of detecting infinitesimal movements. As the plate approached within micrometers of the lens, any Casimir force would deflect the pendulum measurably. The experiment required meticulous control of environmental factors. Temperature variations, vibrations, electromagnetic interference, all could overwhelm the tiny signal. After months of careful measurement, Lamoureux obtained results. The attractive force existed exactly as Casimir had predicted. 48 years earlier, the measured values agreed with theoretical calculations within 5% accuracy. The discovery validated quantum field theory in remarkable ways. It proved that vacuum fluctuations weren't merely mathematical conveniences, but real physical phenomena producing measurable effects. Yet this was only the static Casimir effect. The prediction that two stationary plates attracted each other. Something far more extraordinary had been predicted decades earlier, and still awaited experimental confirmation. In 1970, physicist Gerald Moore proposed a radical extension of Casimir's work. Moore theorized that if a mirror moved at relativistic velocities, approaching 10% of light speed, something extraordinary should occur. Virtual photon pairs normally appear and annihilate so quickly that they remain unobservable. But if a mirror accelerated fast enough, the changing boundary conditions would prevent some virtual pairs from recombining. They would become real photons. With measurable energy, light would emerge from vacuum itself. Moore called this the dynamical Casimir effect. The prediction was theoretically sound, but practically impossible. No technology could accelerate a physical mirror to the required velocities. The forces involved would vaporize any material. Moreover, achieving the necessary acceleration over distances comparable to photon wavelengths seemed fundamentally unachievable. Moore's idea joined the collection of fascinating but experimentally inaccessible predictions in theoretical physics. For 40 years it remained in that category, elegant mathematics describing phenomena that could never be observed, until a team in Sweden recognized something crucial, that the problem could be solved by redefining what constituted a mirror. They didn't need to move physical matter at impossible speeds. They needed to change the electromagnetic boundary conditions at those speeds, and superconducting quantum circuits provided exactly that capability. In May 2011, Christopher Wilson and Per Delsing at Chalmers University achieved what had seemed impossible. Their experimental apparatus didn't involve any moving parts in the traditional sense. Instead, they used a squid, a superconducting quantum interference device. The squid functioned as an artificial atom with adjustable properties. By modulating the squid's magnetic flux at microwave frequencies, they could vary the electrical length of a transmission line. This created an effective mirror that oscillated at enormous speeds. The modulation frequency reached 11 gigahertz, billions of times per second. When the team activated the system, something remarkable appeared. Microwave photons emerged from the resonator. Real particles with measurable energy materialized where none had existed before. The photons exhibited quantum correlations, two-mode squeezing, a signature confirming they originated from converted vacuum fluctuations. The team published their results in Nature in November 2011. They had observed the dynamical Casimir effect, photons created from quantum vacuum itself. Understanding how this doesn't violate conservation of energy requires careful examination. Classical physics, vacuum means absolute emptiness. Quantum mechanics revealed something profoundly different. Even in perfect vacuum, quantum fields maintain irreducible fluctuations. Virtual particle pairs constantly appear and vanish. These fluctuations produce measurable effects. The energy associated with these fluctuations is called zero-point energy. When the Swedish team created real photons from vacuum, they didn't violate energy conservation. The energy came from the squid's mechanical motion. Modulating the electromagnetic boundary required input energy. That kinetic energy converted into electromagnetic energy of real photons. The vacuum fluctuations acted as an intermediary. They provided the mechanism for conversion, but didn't supply the energy themselves. This distinction is crucial. The experiment demonstrated that vacuum contains structure and dynamics, but it didn't prove vacuum is an infinite energy source. The photons emerged because energy was actively pumped into the system. For nanotechnology, understanding Casimir forces became critically important. At nanoscale dimensions, these vacuum-induced forces can dominate other interactions. Despite these advances, fundamental mysteries remain. Researchers still debate whether practical energy extraction from vacuum will ever prove feasible. More troubling is the cosmological constant problem. Quantum field theory calculations suggest vacuum energy density should be enormous. Yet observations indicate it's extraordinarily small. This discrepancy represents one of the most severe disagreements in physics. The fundamental question persists. What is quantum vacuum really? Is it truly a seething foam of virtual particles, or merely a useful mathematical description? Experiments provide data points, but complete understanding eludes us. What the Swedish experiment ultimately demonstrated was that nothing doesn't exist in quantum mechanics. Empty space is not empty. It maintains intrinsic structure and dynamics. Governed by quantum principles, the team didn't violate physical laws. They revealed that reality has layers we're only beginning to understand. The discovery doesn't promise revolutionary energy sources. It offers something more valuable: deeper understanding of how reality functions at fundamental levels. The journey from Casimir's theoretical prediction to experimental confirmation took 6 decades. We thought vacuum was nothing. It turned out to be everything we didn't know how to see. Empty space is where the universe keeps its most fascinating secrets. If you liked what you just saw, like the video, subscribe to the channel, and activate the bell. Leave your opinion in the comments below to let me know what you thought. Thanks for sticking around, and see you in the next video.